So let's talk about the rationale behind GANs in a little more detail now. Let me remind you what GANs are doing. That basically you have a generator that is trying to fool a discriminator. First, let me write the discriminator down. What is the discriminator trying to do? It's trying to distinguish between real data, X, that is being fed to it. You might think of it as a binary classification problem where there's real data X, and then there's artificial data coming out of the generator. Let me draw the generator here. Generator G, that is being fed a latent vector, drawn from some convenient distribution. So let's think of it as Gaussian with zero mean and identity covariance. So there's this artificial data G of Z coming out, and the discriminator is basically trying to do supervised learning, right? Because we know which data is real. We can assign a label y equals 1 to it. We know which data is artificial. We can assign label y equals 0 to it. The discriminator will output y hat, which will be in 0, 1 as usual. We'll train it using a cross entropy loss, and the most simple framework of playing the game would be that the generator minimize this is what the discriminator does, and you want to maximize this, and that's what the generator does, right? So that's the simplest way of thinking about this game that they're playing. They're just playing to one of them is trying to maximize something, the other one is trying to minimize something. Okay, so what does this cost function look like? Well, it's simply the cross entropy cost. So remember that for a single data point, the cross entropy when the true label is y and the estimated probability of class 1 is y hat is minus y log y hat minus 1 minus y log 1 minus y hat. So for a true data point, what do we have? We have y equals 1. So the second term goes away. And what is y hat? Y hat is just the discriminator operating on true data, right? For artificial data generated from a random vector z, what is fed to the discriminator is g of z. My y is equal to 0. My y hat is d operating on g of z, right? So let's see, let me change pen color. The cross entropy cost function for true data would become, if I look at y equals 1 term and plug in this guy there, what you'll get is minus log d of x, and for true data point, and if I have artificial data, then y is 0, and so the first term goes away. So I have this box term here, and this is my y hat. So I have minus log 1 minus d g of z, right? So basically, if I look at the cost function to be minimized by the discriminator, let me change back to blue pen. There's basically a cost function, that depends on both the parameters of the discriminator DNN and the generator DNN. From the point of view of the discriminator, the cost function to be minimized is summation over all the sort of data examples that you're feeding it, and that might be just a mini batch of data that you feed it for each sort of time that you update the coefficients. So that's the contribution due to the true data points, and you also in your mini batch will have a bunch of artificial data that I'm going to sum over the vectors z that generated, latent vector z that generated, and that is going to be 1 minus d of g of z inside the log, right? So let me box this and say, okay, this is what the discriminator is trying to minimize, and of course the generator will try to do exactly the opposite, right? So minimize over theta d and maximize over theta g. And this is a minimax game, and actually if we were actually able to maximize or minimize over the entire parameter space in one go with all the examples in there and all the artificial data in there, the order of maximization and minimization would actually matter. But here basically all we are doing is we are taking one step or some number of steps in adapting the discriminator coefficient and some number of steps in adapting the generator coefficients, and that's how we proceed, and there's no pretense that we are actually getting to the global optimum of anything, really. So we are going to converge to some sort of local optima for each, otherwise things would keep changing, and at that point hopefully we'll have a good solution. That's the usual approach that we have for DNNs, except this is actually more tricky because you're maximizing over one set of parameters and minimizing over the other. So in practice, there's one more thing we need to worry about. Well, while the discriminator that we are training, that's just basically a standard supervised learning exercise, right? And it actually turns out it learns pretty fast at the beginning how to, distinguish between real data and artificial data, especially because the generator is not that capable yet, right? So what happens when that happens? So let's look at it. The generator actually gets into trouble. So let's look at what happens at the last layer of the discriminator, which is, I'm making a binary decision between real and fake data. So you have y hat going in. Let's say I call u the term that is going into the input, and let's look at the standard cross entropy cost function. As usual, I just need to look at one example, and gradients just add up, right? So this is my cross entropy cost function, and we had already done, and let me call this L1 because this is what I would use as my first choice. And I actually know what when I backpropagate through the sigmoid, what this guy corresponds to, the partial derivative of this loss function with respect to the input to the sigmoid is simply y hat minus y, basically there. So what happens for when the generator is losing the battle? It's got to use this gradient to adapt itself, right? So let me change pen color. When the generator is losing, basically y hat is approximately equal to y when d is winning, or equivalently g is losing, which means the gradient is small, which means it's hard to adapt anything. The discriminator is happy because it's winning, so I don't need to adapt it. But the generator is losing, so it should adapt, but it's hard to adapt. So the approach that is suggested in the papers is to let the discriminator still minimize the cross entropy loss, but modify the loss function being optimized by the generator so that we still have a decent gradient when the generator is losing. So let me redraw the sigmoid again. There's my input, there's my output, and what the generator wants to do is sort of maximize the y hat. So the true y is 0, remember. So it wants to maximize the y hat when I'm feeding artificial data in, right? So, an alternative loss function that's been proposed is log of y hat, right? So basically I'm trying to maximize that. When I compute this guy, the gradient for this guy with respect to the input, that is pretty easy to see. It's 1 minus y hat when you backprop through the sigmoid. Now what happens when the generator is losing? Well, when the generator is losing, let me again change pen color. When G is losing, and so D is winning, the discriminator is winning, y hat is approximately equal to the true level 0 for the artificial data, right? So, but now the gradient is good, but we do have a decent gradient, which means the generator can adapt, right? So the details are sort of formally written down in the handout, but this is the main idea of the cost functions that are used for adapting these things. Of course, in actually making GANs work, there's a lot of experimentation that needs to happen with architectures, and the first paper to really scale GANs to images and using convolutional networks was this so-called DC-GAN paper that again I've provided reference in the handout. So let me make some theoretical observations about what might happen with GANs in the best case scenario. I mean, it's really making them work is about playing with parameters, hyperparameters, and a lot of trial and error. But what happens in the best case scenario for the discriminator and generator? So I'm going to call this sort of theory in quotes, because this is just what you would like to happen in the best case. So what's the optimum discriminator? Let's think about that. We already have a background in hypothesis testing, so we know actually what the answer actually should be. So what I have is I have real data X that comes from some density that I'm calling P data. And then I have artificial data, and from the point of view of the discriminator, it doesn't really know that it's artificial data, right? So it just has, it sees some X in the data space, but hopefully it comes from a different distribution. I'm going to call it P sub G of X, right? And how close this is to P data of X is just how complex your generator is, how well you've been able to train it, etc., right? So suppose these are the, for the frozen generator right now, these are what you have, and you were training your discriminator. What's the best you can do? Well, what does the discriminator produce? It produces y hat. And what is y hat? Optimal value really is going to be, what's the probability that it's real data given what you're seeing, right? So let me change pen color and write down the labels here, right? When I'm training it, or the hypotheses really are labeled 1 for real data and 0 for fake data. And so this guy, the Deopt, which is this posterior probability, I can write it as using Bayes' rule, right? P of X given Y equals 1 times the probability y equals 1 divided by P of X, which I'll write out again using the law of total probability, that this is just that first term on top, and then I have the corresponding conditional density given y equals 0 times the probability y equals 0, right? So I'm assuming that the prior probabilities of real data and artificial data are the same. So all these probabilities, these prior probabilities are equal to half, and they cancel out, right? So I'm going to cancel them out, and then I'll note that this guy is just my p sub data of x. That's what I was calling it. And this guy is my pg of x. That's what I was calling that. So I can write Deopt of x equals plugging out everything else in p data of x divided by p data of x plus p generated of x. Note that we have shown the same thing by direct differentiation in the handout, but and I'll let you take a look at that. But it's nice to know that the cross entropy cost function is minimized by exactly the right thing that that Bayes rule would tell you. So once we know the optimum discriminator, what would the optimum generator be? So let's look at the cost function to be minimized by the generator. So let me write it down. Cost function to be minimized by the generator. Well, that's just the expected value of the cross entropy function, right? So basically the expected value of the negative of the cross entropy function, right? So that's the generator's cross function. J sub g is the negative of the cross entropy function, and I'm going to take the expectation over both real and artificial data. So I have y log y hat plus 1 minus y log 1 minus y hat, right? That's what this guy is. And when I average this out over real data, well, real data happens with probability half, and y is equal to 1, and so 1 minus y is 0, so the second term goes away. So I have log of y hat in there, so I have log of y hat, and y hat is just a discriminator operating on the data, times averaged out using p data of x dx, right? That's the part of the expectation that comes from real data. And with probability half, you have generated data, and so you have for generated data, my y is equal to 0. So 1 minus y is 1. So I have the second term here. So I have log of 1 minus y hat, which is d of the data presented to me, and that data has density this p sub g of x, right? So that's the cost function I'm trying to minimize at the generator. Let me plug in now the optimum d of x, but before I do this, let me get rid of these half terms that really don't matter in terms of the optimization, right? So I'm just going to get rid of them. So I'll keep the same notation, j sub g, after getting rid of those guys, and plug in the optimum discriminator that I have. So I have, and I'll put both those terms together. So I have log of, what's the optimum thing? P data of x over p data of x plus p g of x, and then that's averaged out using p data of x dx, right? That's the first term that I have. The second term is log of 1 minus Deopt of x, and that you can see immediately it's going to be the other guy on top, pg of x, and then the same denominator, p data of x plus pg of x times pg of x dx, right? And when I look at, let me just look at one of the the first term, what is it? It's expected value evaluated using p data of log of p data of x over. Now, if I want to make this sum in the denominator, this guy, a density, I know that both of them integrate to, each of them integrates to 1. So when I sum them up, that's integrating to 2 over x. So I'm going to divide by 2 and get a density, right? So I have this happening here. And if I divide by 2 here, I have to also have a factor of half in the numerator that gets rid of that, right? So this is my only the first term I'm writing. That's, the other term is very similar. Well, let's look at what this guy is. This is the expected value of log of p over q. It's expected value using p of log of p over q. What's that? That's just the divergence. It's the divergence between p data and the average of the p data plus p generated distribution. So that's coming from this term. And this, the half term, let me change pen color to highlight that. That's just a constant, right? And the log of half is minus log 2. So there's a minus log 2 there, right? The other term is exactly analogous. This term is just going to be the other thing. So exactly symmetric thing. P sub g, the divergence of that with the averaged guy over 2. Again, minus log 2. Again, that doesn't really matter, right? Have a factor of half in the numerator that gets rid of that, right? So this is my only the first term I'm writing. That's, the other term is very similar. Well, let's look at what this guy is. This is the expected value of log of p over q. It's expected value using p of log of p over q. What's that? That's just the divergence. It's the divergence between p data and the average of the p data plus p generated distribution. So that's coming from this term. And this, the half term, let me change pen color to highlight that. That's just a constant, right? And the log of half is minus log 2. So there's a minus log 2 there, right? The other term is exactly analogous. This term is just going to be the other thing. So exactly symmetric thing. P sub g, the divergence of that with the averaged guy over 2. Again, minus log 2. Again, that doesn't really matter, right? So these are just constants. So what do I have? That my j sub g is d of p data and then this averaged guy, p data plus pg over 2 plus d of pg and then again the p data plus pg over 2. And then I'll ignore the minus 2 log 2 term that is there. But look at this. We know that the divergence, the KL divergence is not symmetric, right? So it's not a real distance this way. So what we have here is a symmetrized version of the KL divergence, which also is 0 only if both the densities are equal. Only if p data and p generated are the same. And this is actually this guy, or at least the average of this guy, is called the Jensen-Shannon divergence. So this is 2 times the Jensen-Shannon divergence between p data and p generated. So what the generator is doing is trying to minimize a symmetrized version of the KL divergence between the data density and the generated density. So it's trying to manipulate the generated density to get as close to the data density as possible. And again, all this means is saying that, okay, minimizing the cross entropy function for the discriminator while maximizing it for the generator leads us to sensible results. And of course, how close we get to these results, how close the PG comes to P data, all depends on how good your optimization procedure is, how powerful your DNN representations are, given the complexity of the data, etc. So all those are matters of detail, but this at least gives you insight saying, okay, it makes sense. The whole thing hangs together. Since GANs were proposed in 2014, there's been a huge amount of work, both on just trying to make them work in various settings, but then also exploring some neat architectural variants of the idea of adversarial training. So I'm going to just briefly sketch a few of them, just like I've done in the handout, and just comment on them. You won't really get much out of it unless you go to the papers and the code. This is just to sort of provide some sort of orientation as to what's going on. So GAN variants, and then really clever variants lead to some very interesting applications. So one of them is, of course, conditional GANs, where you have the same game played by the generator and discriminator, but you also provide some side information, right? So, and the particular kind of side information you provide, so depends on the application, and depending on that, you are able to generate different kinds of information, right? So the generator still generates artificial data, and I still have real data coming from here, G of C going to there. There is the discriminator still as before, but now the discriminator also has access to this side information. What could the side information be? Many things. I mean, one possibility is just to provide labels. So if I, for example, look at the MNIST data set, which is digits, if in addition to providing pictures of the digits, you also provide the label for the digits, then maybe you can generate the specific digits for artificial data resembling MNIST for specific digits that you put in as side information using the generator rather than something picked out of one of the 10 digits. More challenging applications could be, for example, suppose my real data is what I want to do, for example, is to translate sketches to photos, right? So what I want to generate is photos, and what I want to input is a sketch. This might be a sketch of a cat that I input, and if I now do that, I can potentially generate photos of cats from sort of vague sketches. So there's a bunch of different things you can do with conditional GANs through clever choices of side information in relation to the actual data, and it's really up to your ingenuity and a lot of blood, sweat, and tears in terms of looking for architecture and hyperparameters and training as to what you can accomplish. Another idea that is really interesting is this notion that we called CycleGAN. So the idea of CycleGAN is, think of the application first. Suppose I want to take photos and render them as paintings in the style of Monet, right? That's a style transfer problem, and there could be other approaches to that as well. So suppose I think of photos as domain 1 and Monet paintings as domain 2, and I would like to translate a photo to something that looks similar to it, but it's a painting in the style of Monet. So what might I do? Well, I might want to take something from domain 1 say a photo domain, and I want to come up with something, a generator that translates it to an analogous Monet painting, right? And I will have to, whether it looks like a Monet painting or not, depends on how hard I have worked to fool a discriminator to which I am feeding real data from domain 2, from the domain of Monet-like paintings. So this is domain 1. But how do I make sure that what I get out does look like that original photo that I put in, that the painting that I get out from here, this G12 of X1, that this looks like a Monet version of that photo I sent in? Well, I can then say I'm going to actually train another generator going in the reverse direction from domain 2 to domain 1, so from Monet paintings to photos. So G of 2 to 1, and that's going to be something in domain 1. And changing pen color, I'm going to insist that these should be close to each other. So this is called the cycle consistency, right? So I'll have a term in my loss function asking for cycle consistency when I do this round. And of course I have the generator discriminator game here, and of course the corresponding game and cycle consistency loss for the other domain, right? So I don't know whether I want to, let me sketch it out quickly anyway. So I basically have exactly the same thing going on. I have something from domain 2, X2, going into the generator that takes things from domain 2 to domain 1. And that's going to be fighting against a discriminator that gets real data from domain 1. So that part is standard sort of adversarial training using a cross entropy loss. But I'll also have this cycle consistency business in the other side. Basically I'll get a x hat of 2 when I take this artificial data that G2 to 1 spit out in domain 1. This is in domain 1. Send it back through the generator that creates a data point in domain 2, and then let me change pen color. Again, these should be close. So I have the loss function will be sum of the GAN loss functions for these guys and these guys, and the cycle consistency loss functions for this and this, right? So I train all of these together, and I've got basically 1, 2, 3, 4 DNNs that I need to train. And people have demonstrated all sorts of really cool applications, and I refer you to the papers that are pointed to in the handout for exploring further. One last thing I want to talk about is fixing a drawback of GANs with respect to VAEs. So variational autoencoders basically take the data and create an embedding. Whereas GANs, all they are trying to do is generate artificial data from random vectors in the latent space. Can we also get embeddings using this adversarial training idea? And that's an idea that's called bidirectional GAN. I'll talk about why it is bidirectional, BiGAN, but I'm going to not write it as a bidirectional picture. So basically, here's what I want. Let me give myself enough room for a picture. So I would like to train an encoder also for the real data. So encoder E, I want to train that, okay? And I want to get an embedding E of X, right? I still have this generator G that takes that takes basically randomly generated latent vectors and spits out artificial data, right? G of Z. And there's a discriminator sitting on top. Discriminator D that is trying to distinguish between the real and the artificial. And now I'm going to give the discriminator a hand. I'm going to make it even more powerful. Instead of giving it just the X and the G of Z, I'm going to give it both the X and the embedding E of X on this side. So basically, I'm going to give it both these things coming into this discriminator. And I'm going to give it the analogous thing here. So I'm going to give it G of Z and Z. I'm going to give those from here. Let me change pen color. These correspond to y equals 1. These correspond to y equals 0. This is the real, and this is randomly generated artificial data, right? So I have given the discriminator a leg up because I'm giving it not only stuff in the data space, but also something in the latent space to distinguish between the real and the artificial. And so in order for the generator to have a chance of winning the game, it has to work together with the encoder. And of course, the gradients have to flow down to train both the encoder and the generator together. So these guys are actually working together, train together to fool the discriminator. So that's the game that we have. And if you succeed, then you're producing an embedding that is not that cannot be distinguished from the latent distribution. And in fact, the joint distribution of X and the latent and the embedding cannot be distinguished from the artificial data and the latent vector that generated it, right? So that's sort of a very powerful idea, and it means that GAN the GAN idea can be extended to also provide embeddings. And of course, the reason it's bidirectional, it's called bidirectional, is because we are going both from the latent space to the data space using the generator, and also going from the data space to the latent space using the encoder. Okay, so that's that for GANs. In order to, basically what we've tried to provide is just sort of the rationale behind GANs and their variants. In order to really appreciate them, you have to actually go to the original papers and play with code. And I encourage you to do that, of course.